Hey then, so I'm now going to do a video on chapter 13 of Colin Mclarty's Elementary Categories, Elementary Toposes. And this is about the basics of topos theory. Now, these are my personal notes, so they may not be comprehensive, especially as far as, understanding the very, very basics, which are far too basic. well, Colin Mclarty's book's fairly laconic, so I, I mean, it's a wonderful thing, but he doesn't go into so much. He doesn't do so much hand holding with the basic definitions, and so you may want to watch my actual video on topos theory to get to grips with the basics. But anyway, I'll just dive right in. So a subobject classifier is an object omega with an arrow t into it from the terminal object. We call that true usually, such that for any monomorphism, say a monomorphism from S to A, actually that should be from zeta to A, any monomorphism S from zeta to A, that's consistent. There exists a unique arrow called chi of S from A to omega, such that S is the pullback of T along chi of S. In other words, we have this pullback square. Okay. Pullbacks are only defined up to isomorphism, and this defines this sort of class of equivalent monics. So when we get T and we pull it back along this classifying arrow chi of S, we get, well, we could get different monics S, but they'll all be equivalent, so we just sort of pick one and that's fine. Okay then, equivalent in the sense that they have precisely the same members. All right. So what this means, and we're working in a topos. Now, a topos is a Cartesian closed category with all finite limits and with a subobject classifier. Subobject classifiers are unique up to isomorphism that can be defined by universal properties, so we can just talk about the subobject classifier. In sets, the subobject classifier omega is just something with two elements, and one of them we call true, okay, because that's the one that we have this arrow from the terminal object into that is like the T, okay. So the basic idea is that given any arrow into the subobject classifier, for example, well, I've got chi S here, but could have another arrow, if we say call it U, then we call the subobject it classifies, or a representative member of the equivalence class of subobjects that it classifies, we call it U star, okay? That's just a bit of shorthand. Now, the critical thing about subobject classifiers, well, there's a couple of things. This is very important, is that when we have this kind of setup, so chi of S is the classifying arrow of this monic S, we actually have that chi of S is the equalizer of, sorry, we have that S is the equalizer of chi of S and exclamation mark A, this unique arrow from A to the terminal object. So let's see if we can see this. So firstly, chi after S from the commuting of this square is T after exclamation mark zeta. But we can also write that as T after exclamation mark A after S, because going along S and then going along exclamation mark A gives us this unique arrow exclamation mark zeta into the terminal object. So we have that S equalizes T after exclamation mark A and Z and chi S. And now given some K, which also equalizes these, we have that chi S of K equals T after exclamation mark T. So we have this kind of picture. And then we have this unique V, because we have a pullback, we have this unique V such that exclamation mark T equals exclamation mark V after V. Well, that's automatic. And secondly, that K is equal to SV. So really we have a unique arrow V such that K is equal to SV. So that means that S is the equalizer that we claimed. Okay. Notice that this is an if and only if statement. So that's pretty interesting, because it means that we can give a sort of equivalent kind of definition. We can give it a kind of equivalent description of the way that sub-object classifiers work. Another interesting thing is that this implies that in a topos, all monics are equalizers, because, well, I've just said they are. Okay. For example, this monic is the equalizer of T after exclamation mark A and chi of S. And also, as I think I've already said in a previous video, if an equalizer, so if we have a monic and it's also epic, that means it's an epic equalizer. And that means since FE equals GE, that means F equals G. And also identity of A equalizes F and G. And so we have that there exists a H such that EH equals 1A. So that means E is split epic. So E has to be monic and split epic, which means it's ISO. So that's a fancy way of saying that in a sub-object classifier, every monic epic is ISO. Just like in the category of sets, okay? If a arrow is monic and epic, then it's ISO. So we see where that comes from now. Right, so now the important thing about S being an equalizer of chi of S and T after exclamation mark A is that, like, an equivalent way to say that is that for any T elements of A, we have the X is in S if and only if X equalizes these two things. So if and only if chi of S of X is T exclamation mark A of X, which is equal to T after exclamation mark capital T, where, you know, it's like this. this is sometimes given a shorthand as T subscript T. Okay, so it's this unique arrow. Well, it's the what you get by following the unique arrow from a terminal object and then going along T. Okay, and sometimes it's just called true. All right, so this is really cool because what we're saying here is that I mean, we can understand now what this sub-object classifier means. Basically, we have that chi of s of x is true, or true after arrow to terminal object, if and only if this x is in S. So this chi here is a sort of function, or a sort of arrow, which is classifying what's in this monic S. Okay, and I mean this x is in S is sometimes said as x is a member of the monic S. All right, and by this I mean that there exists a k. So x is in S means there exists a k such that x is equal to sk. Okay. Another important thing to note is that this arrow, this monic, which is the identity, sometimes called the maximal subobject of T, one T that is, this identity arrow, its classifying arrow is T after exclamation mark T, as can be seen by noting that this is a pullback. Okay, so clearly this square commutes, and given any H with arrows U and L, which make things commute, which makes the outer perimeter commute, we have that L is the unique intermediary arrow, which makes the whole diagram commute. So yes, this is a pullback square, and since then we have that 1 T is the pullback of T along T exclamation mark T, we have that T exclamation mark T is the classifying arrow of this identity arrow of T. Okay, so that's cool. I mean, that's basically saying that when this classifying arrow is kind of unanimously true, then the monic it's classifying is the one that has everything in it. So we can sort of think of the classifying arrow as categorizing the bits which are there. Okay, so anyway, the next thing to note we have this sort of what's called the generic. So this arrow T from 1 to omega is sometimes called the generic subobject, and there's also such a thing as the generic pair of subobjects, and what they are is this subobject, which is T times 1 of omega, like this, and also the other one, which is 1 omega times T, which is like this, but with the objects in this product at the top swapped around, okay? And so I am showing here that the classifying arrow of this particular one of the generic pair of subobjects is just the first projection, and similarly the second projection works in the other case. So is this clear? Like we can rewrite this as TQ1, Q2, and then doing P1 after it gives us TQ1. So this square commutes, and then given a candidate which also makes the outer diagram commute, we'll have to have that this arrow is T exclamation mark H comma beta, and if we set this arrow to be exclamation mark H beta, well, it has to work like so. All right, so we've got that now. So the first thing then is that there's a unique arrow U. This is theorem 13.2. There's a unique arrow U that makes this square commute and also makes it makes this a pullback, excuse me, on the left, and also it makes this a pullback, which is the same thing with the other one of the generic pair of subobjects. It should be 1 times omega with an arrow like that. So there's a unique U which makes these two squares pullbacks given monics R and S, and in fact that U is chi S, comma, chi R. This is building up to a kind of definition of AND. Okay. So how can we see this? Well, consider this this thing here, all right? So we know that the right squares are pullback. I just demonstrated that. So then the pullback lemma means, which I discussed in my video on pullback theorems, is that this whole outer rectangle is a pullback if and only if this left square is a pullback. Now, setting U equals chi r chi s makes the outer rectangle a pullback. Sorry, makes this left square a pullback, so it makes this whole rectangle a pullback. And so, since there's a unique classifying arrow that makes this a pullback, that means that P1 after U has to be that unique classifying arrow. So, and in a similar way, we can do similar reasoning about S. So we find out that U has to be chi r, chi s. That's the basic idea of proof. Next result is that this is theorem 13.3, is that the intersection of this generic pair of subobjects is t comma t. So we see this with this pullback square here. So we have this pullback with a terminal object at the top left and these arrows 1 comma t and t comma 1. And we see that this is a pullback square. So t times 1 after this is going to be tp1 comma p2 after this, which will be t comma t. So this diagonal is t comma t, which is the intersection of t times 1 omega and 1 omega times t. And we can see that this is a pullback because if we have a candidate H that makes this outer diagram commute, then the first component has to be this arrow to the terminal object. If the second one is beta, then we have to have that beta equals t after the arrow to the terminal object, and similarly we have to have that this upper arrow here is also, well, it's a swapped round version. It's t exclamation mark h comma exclamation mark h. And so that means that there is just this unique t. That means there is just this unique. That means we want there to exist this unique arrow. Well, exclamation mark h does the job, and it's obviously unique. So that shows that this is a pullback, and then the diagonal is t comma t, which is the intersection. So that proves that. So now we define the conjunction or and operator to be the classifying arrow of this monic t comma t. And when we do and after a couple of arrows u and v from t, we write that as and after, well, we should write that as and after u comma v, but sometimes we use this notation instead, u and v. And so u and v is true if and only if u is true and v is true. And we can see that because we've got the and after u comma v is equal to true, as in t after exclamation mark t, which is chi of t comma t of u comma v is equal to true, is equivalent to saying that u comma v is in t comma t, which is equivalent to saying that u equals exclamation mark t, sorry, t after exclamation mark t, and v is equal to t exclamation mark t. So indeed u and v is true, which is what this means basically in shorthand, if and only if u is true and v is true. So it acts like a logical and, all right, and we'll but the cool thing is that it really sort of it really characterizes the intersection of subobjects. Okay, so if we do the pullback of this true arrow along v, we get v star. So v star is the subobject that v classifies, and similarly with w. Now the big claim is that the classifying arrow of the intersection v star intersection w star is v and w. So how to see this? Well, it's helpful to look at a diagram of what's going on. So Here we have a sort of illustration of the definition of this AND statement, this composition. Well, I'm basically writing the same thing here, but with R's and S's instead of V's and W's. So this is the statement I want to prove, that for any T elements X I think that should be X of A there. For any T element X of A, we've got that chi of S and chi of R of X is true. I think that should be a T of T there. If and only if chi of S of X is true and chi of R of X is true. So basically, we've got this kind of system. We have these monics, R and S. They're subobjects of A. There's actually another subobject of A, which is R intersection S, which is going to have a role to play. But, you know, critically, we have these monics R and S, and they have these classifying arrows, chi of R and chi of S. We can pair them together to get this arrow into omega times omega. And then if we do this AND operation, composing these two horizontal arrows, we get chi of R and chi of S. And we're saying that doing that arrow on this generalized element, or T element X of A, is going to give true if and only if doing chi of R on X is true and doing chi of S on X is true. So this is a nice proof of it. And this is basically showing that, I mean, what this is basically showing is that this composition here of these horizontal arrows is just the classifying arrow of R intersection S, because R intersection S has exactly this property that X is, for this generalized element, X is in R intersection S if and only if X is in R and S is in S. So since monics are classified by the since monics are classified by the generalized elements which are members of them, as in if we always have, you know, for such a for any T and for any X, we always have X is in monic A if and only if X is in monic B. That means monic A and monic B are equivalent, isomorphic in some sense. Anyway, this is the argument. This is quite sweet. So we have that X is in R intersection S if and only if X is in R and X is in S. That's just using the basic properties of intersection. Now, that's going to be true if and only if chi of R of X is true and chi of S of X is true, using the property of subobject classifier as equalizer. And that's going to be true if and only if chi of R X, comma chi of S X is T, comma T, exclamation mark T. That's just pairing these statements together. And that's going to be true if and only if chi of Rx, comma chi of Sx is in T, comma T, because exclamation mark T is the only possible conduit. And that's going to be true if and only if and after chi of r of x, comma chi of s of x is true. That's because and is the classifying arrow of t comma t. And then just rearranging a bit, we can write this as chi of r and chi of s of x is true. So the bottom line of this is that if we have the r intersection s, if we have the r intersection s is the pullback of true along phi, in other words, if phi is the the bottom line of this is that if this arrow chi of r and chi of s of x, which is this arrow we get by following these sort of roughly horizontal arrows along, if that is true, well, let's suppose that that long arrow is the what I'm saying is that if we suppose that this horizontal arrow, so just these two, so and after chi of r comma chi of s, if we assume that that's the classifying arrow for some monic phi, then that monic phi is equivalent to r intersection s, because this statement here would be equivalent to saying that x is in phi, where the classifying arrow of this monic phi is chi of r intersection chi of s. And that means, of course, that phi is equivalent to r intersection s, because we have that x is in phi if and only if x is in r intersection s. And when two monics have this kind of condition for any sort of generalized elements into their generalized elements of their codomain, then they're equivalent monics. That's the corollary on page 40 of Colin Mclarty's book. So there we go. That basically means that and is like intersection in a very precise sense. In the sense that chi of r and chi of s is the classifying arrow of the intersection of r and s. And then we can connect with lots of nice results about intersections. Because, for example, if we have this, well, we know, for example, that u star intersection u star is u, because because x is in u star if and only if x is in u star and x is in u star. And that means, going sort of converting to arrows into the subobject classifier, we get u and u equals u, which makes sense logically. We also have, because u star intersection v star is v star intersection u star, we have that u and v is v and u. And we also have that u and true is u, because u star intersection identity is u star. Okay, so let's now get on to something more, something different. Let's define this less than or equal to arrow, sometimes called less than or equal to 1, with subscript 1, as the equalizer of and the first projection. So now notice that for any t element, x comma y of omega times omega, we have x is in less than or equal to, sometimes written as x is less than or equal to y, but anyway, x is in less than or equal to if and only if, we have that x comma y is in less than or equal to, sometimes written as x is less than or equal to y. Anyway, we have that x comma y is in less than or equal to if and only if x comma y equalizes these two blue arrows up here, in the sense that x and y is equal to x. So now shifting into monic speak, doing the pullback of true along the classifying arrow, the logical way to say this is that y is at least as true as x, but the kind of subobject way to say this, more precisely, is that x and y is x, but pulling the true arrow along along each of these equal things, we get that x star intersection y star is x star, where x star is the monic classified by x. And now thinking in terms of generalized elements, this means that v is in x star and v is in y star if and only if v is in x star. And that's equivalent to saying that v is in x star implies v is in y star, which is equivalent to saying that x star is contained within y star. So the bottom line is that when we have precisely when we have the x comma y, these two kind of arrows into the subobject classifier, when they're paired together, when x comma y is in this less than or equal to, that's equivalent to saying that x star is a subobject of y star, or x star is in y star, or x star is contained in y star. Okay. So, I mean, this here, that's less than or equal to, is just in, but when both of the things involved are monics, we write this contained in symbol instead, a subset symbol. Now, the next thing is that obviously if it's less than or equal to thing, since it's an equalizer, it's a monic, and we can consider the classifying arrow of that monic. And sometimes that's called the material conditional arrow. So it acts sort of like implies. Okay. So here's the critical thing, sort of defining it. We have that x is less than or equal to y. This is for t elements, x and y of omega. We have that x is less than or equal to y. That means that x comma y is in less than or equal to. And we've already sort of argued that that means that x star is contained in y star. But anyway, this x comma y is contained within less than or equal to. Another way of saying this is that doing the classifying arrow on less than or equal to on x comma y gives true. That classifying arrow is called this material conditional arrow, little arrow. So that means that little arrow x comma y is true, which is sometimes written as x material conditional y is true, or x implies y is true, if you want to be a bit sloppy. But I'll call it material conditional because I'm going to use implies in a more meta kind of sense. Now, suppose we have a setup like this. So we have these arrows, these monics, these subobjects, R and Q of A, and they have their classifying arrows, chi of R and chi of Q. And we can form this kind of setup using this material conditional arrow. So material conditional after chi of R comma chi of Q, which is sometimes written as chi of R implies chi of Q. So then we're interested in, well, that's an arrow into subobject classifier omega. So which subobject does that classify? And it turns out to classify this one, which we call Q implies R. Okay, or Q double arrow R. So we want to understand Q double arrow R. And this result lets us understand it. So it says that for any monic, for any subobject S of A, we have S intersection Q is contained in R if and only if S is contained in Q double arrow R. So I've got a picture of this somewhere. Basically, the picture in terms of set theory is that Q double arrow R looks like this. It's the set of all stuff that's intersection with Q is contained in R. Okay, so whenever one of these things is in Q, it's in R, hence Q implies R being the sort of symbol for it. Okay, so that's the basic gist of this theorem, which we want to prove, theorem 13.6. And so here we go. This is a hard one, I think, or at least it's not easy to read in Mclarty's book. It's one of those where he's a bit too laconic for his own good. It's like, well, anyway, so S is contained in Q double arrow R. What's that mean? Well, that holds true if and only if chi of Q material conditional chi of R after S is true. We can take this material conditional arrow out to the left. We can put this S inside the brackets. And so then using, how this material conditional arrow is defined as the classifying arrow of less than or equal to, we see that this is equivalent to saying that chi Q of S, comma chi R of S is in less than or equal to, which is equivalent to saying that chi QS is less than or equal to chi RS. And now the next step in logic is pretty huge. So I actually had to establish a lemma to get this. And here's the lemma. It's a general thing that when we have a when we have that chi Q is the classifying arrow of this monic Q, we then have that the pullback of that Q along another arrow S. So we could actually just call this, so I'm talking about this arrow M, which we could also call S to the minus 1 of Q. It's kind of inverse image. That that is going to be the mnemonic classified by chi q after s. So how can we see this? Well, we know that the right square is a pullback. If we define m is s to the minus 1 of q, then we also know that this left square is a pullback. So the pullback lemma gives us that the whole outer rectangle is a pullback, and then the definition of subobject classifier means that chi q after s must be the classifying arrow of m equals s to the minus 1 of q. So there we have it. How does that help us? Well, that means that when we kind of do the pullback of true along these two arrows here, we kind of convert them from arrows into the truth object. Truth object's another name for subobject classifier. We convert them from arrows into a truth object to mnemonics. We go from this statement here, which is chi qs less than or equal to, well, we start with this, okay? We have chi qs less than or equal to chi rs. That's as far as I got down up to here, okay? And now this thing on the left is the classifying arrow of this mnemonic s to the minus 1 of q, and this thing on the right is the classifying arrow of this mnemonic s to the minus 1 of r. So this statement here, s chi q of s less than or equal to chi r of s, is equivalent to saying that s to the minus 1 of q is less than or equal to s to the minus 1 of r. Now we want to show that this is equivalent to saying that s intersection q is contained in s intersection r. Mclarty goes all the way to here in one step, so maybe there's a trick that I'm missing here, but anyway, I did get there. So how can we see this then? Well, s to the minus 1 of q is contained in s to the minus 1 of r. That means there exists a k such that s to the minus 1 of q is s to the minus 1 of r after k, as is shown over here. And now that means there exists a k such that s after s to the minus 1 of q is s after s to the minus 1 of r, but s to the minus 1 of q is just s intersection q by definition of what intersection is. And similarly, s to the minus 1 of r is s intersection r, so we have that s intersection q is in s intersection r. So we've shown that the blue statement here implies this bottom black statement. Now conversely, suppose this bottom black statement, s intersection q, is in s intersection r. Now, given v in s to the minus 1 of q, by the way that inverse images work with generalized elements, we have, or members, we have that v, which we'll define it, sorry, w, which we'll define as sv, has got to be in q. We also trivially have that w is in s, So as you can see here, so W is in S intersection Q. Now, since we're assuming this, we get that W is in S intersection R. So W is in R, and W is SV, and so V is in S to the minus 1 of R. So we've now shown that given this black statement here, we have this blue statement. So finally, we've got this next step in our argument. That S to the minus 1 of Q contained in S to the minus 1 of R is equivalent to saying S intersection Q is contained in S intersection R. Now this is equivalent to saying that whenever W is a member of S, W is a member of Q, we have that W is a member of S and W is a member of R, and that's equivalent to saying that whenever W is a member of S and W is a member of Q, we have that W is a member of R. So in other words, this black statement here is equivalent to saying that S intersection Q is contained in R. So we've finally got our result. So let's have a look at our initial claim. Yeah, it was that S intersection Q is contained in R if and only if S is contained in Q double arrow R. Since S is contained in Q double arrow R, means this. So finally, what this all means basically is that the stuff that's in Q double arrow R is the stuff that's intersection with Q is contained in R. Okay. We could say it's a maximal subobject like that. The maximal subobject S, such as this. Okay. So this is basically the idea of implies. I mean, intuitively speaking, I'd say maybe the most useful stuff is this, that X is less than or equal to Y, which we can think of as saying that Y is at least as true as X, is equivalent to saying that X material conditional Y is true, or if you like, that X implies Y. By the way, this double arrow here, when we're talking about the subobjects instead, is often called the material implicate. Also note, using this result with S is equal to this material implicate thing, we get that Q double arrow R intersection Q is contained in R. We see this here, the intersection of this green area with Q is contained in R, okay? And we could say it's the maximal thing like that. Anyway,